All right, thank you for coming for my talk. It's great to be here. It's my first time at PyData, and it's been exciting to see all of the cool stuff that's going on. And today I wanted to share a little bit about what we're trying to do in academia in my group. I should say that I'm giving this talk on behalf of Vaggelis, who couldn't be here today. So he's, why is this not showing? He's the guy to the right here, together with the rest of the team, Laura, Edo, and Gemma. We're maintaining the core imaging library, or CIL. All right, so what is the CIL? It's an open source Python library for solving inverse problems, so imaging type inverse problems. And in particular, we have a special emphasis on tomography applications, so CT scan type setups with kind of challenging data sets. So if you can't get away with the standard method, if you have poor data, low count data, some non-standard setup, incomplete data, or otherwise a challenging setup, this is the kind of case we're looking at. It's highly flexible, modular, offers a number of different tools for doing CT and other kinds of imaging. And in particular, we have we call it a near-math specification and solution of optimization problems as part of this package. We think it's quite simple to get started, yet powerful enough to actually handle large data sets, real applications. It's funded by a UK initiative called the CCPI, and it's released under an Apache v2 license, and it's all on GitHub. So what I'll cover today, I'll be talking a little bit about direct and inverse problems. I'll have a few demos, and if you're interested, you can go and type along for the first one at least. You can go to this link and launch the binder. Should be up and running. Then I'll talk about the inverse problems and how we solve them, and the rest of the demo. Move on to talk about CT imaging a bit more in particular, and then talk about, have another demo, and finish with showing some of the cases we've been working on where we've been able to improve the imaging. All right, so let's get started. So first of all, what is an inverse problem? And in a kind of general context, you can think of we're interested in determining some parameters, some object. This would typically be an image, but we don't have access to it. So what we do, basically, this image gives rise to some data, some measurements. So those are the data, we can obtain those. And the direct problem is how the object is mapped to the data. And the inverse problem is then going the other way. So how do we, from the measured data, go back and obtain the quantity we're interested in? And we typically write it as this kind of mapping. So we have an operator here, a forward or a direct operator that maps the image to the data. And I've got a couple of examples here. So one case is image deblurring. So the direct problem would be, assume we know an underlying kind of sharp image. That's what we want to estimate. But we only observe the result of the direct problem, namely the blurred image over here. And our task is then to solve the inverse problem of recovering the sharp image from just the observed blurred image. Another case could be images where parts are missing. So this is sometimes called inpainting, or filling in the blanks of this image. So this is the kind of true image we don't have access to. I guess you don't see my pointer here, but to the left, what we observe is the result of the direct problem, namely the corrupted image to the right with some parts missing and some noise also, and we want to solve the inverse problem of going back and obtaining the image over here. The last case I've got today is CT imaging, so computed tomography, and here we have some object. Here I have a two-dimensional image. What we do is we rotate it and we acquire X-ray projections of this image. And each projection here looks like this maybe, and we stack them all together into what's called a sinogram over here. This is our measured data, and then again we want to solve the inverse problem of going back and recovering the image. So that's what it looks like. And I'm going to switch to the first part of the demo. right here, hoping that it still works. Did when I was just testing right now. So we'll be looking at, I think I need to, let's see, switch this off and go here. All right. Right, so we will be looking at a case of deblurring, so recovering a sharp image from an observed unsharp image. So from our library, from SIL, we import a number of different tools we need. That's the starting point. We can set up some different test images, some boat and camera, some of those kind of usual test images we use in this field. One of them is a resolution chart, and we see what we get is something two-dimensional of the shape 256 by 256 pixels in the X and Y dimensions. We set up a display function that we can use throughout to get consistent plots and show our image. So this is what the kind of true image that we wouldn't have access to looks like. Okay, so this is an image. We have a special data type for that. We call it image data, and it kind of contains some additional information about the size and how big are the pixels and so on. So we hold that in our image data class here. And in particular, we have something we call the geometry, which is where all this extra information is stored. Where is it located, and how big is everything? Okay, so our setup is the following. So assume we knew the image, then we will be mapping that through an operator here. This will be our blurring operator, and then we'll be adding some noise to that. So that's some Gaussian noise in this case, and then this is what we observe. This is our data. In this particular case, for the deblurring, what we do is we apply some point spread function. This is kind of a blurring kernel. It looks like this. We kind of move that across the whole of the image, and that's what will generate our blurred data. In order to do that in SIL, we need to set up this A operator here. So we have an operator class for that, and we give it the point spread function, and it also needs to know about the geometry of the image we're looking at. So that will be our A here. Then we apply it. So we say basically do the direct problem of the underlying true image, which will give us our blurred image. So we get it here, and we see it's been blurred. And on top of that, to make things a little bit more difficult, maybe we didn't observe a clean image. Maybe we had some noise added to that. That's typically the case. And we can simulate that by this Gaussian function here. We take the blurred image and we generate some random Gaussian noise and apply it here. Okay, so this was basically the direct part. We've started from a true image. That is what we want to determine in the end. So we kind of forget about that and just work from the observed blurred and noisy data here. Okay, I'll switch back to the presentation now. Right here. So how do we do that? How do we solve such an inverse problem? So basically, it's kind of a linear problem. Typically, we've got here, this is our setup. It can be nonlinear as well, but in this case, it's a linear problem. So it's basically a matrix vector equation here. But the problem is there might not always be a solution, or you might have so much noise that you can't just do a simple kind of matrix vector solution here. We might have no solution. It might not be stable. There can be tons of different problems. So we call this an ill-posed problem. And we'll see some of the difficulties in solving that in a minute. So this ill-posedness, we have like various parts that are difficult. We have the errors. Maybe our model is not perfect, of a perfect description of what happened in reality. And maybe we also have noise, as I showed, the Gaussian noise in the data. What we do, so we move from this problem here and say we probably can't solve this problem exactly. Also, we have some noise there. So what we do instead is we set up some optimization problem. And this optimization problem we want to solve, and the solution will be our best image. This will be our reconstructed image. So we have two parts normally. One has to do with fitting to the data. So this is kind of a regression term. Typically, we take that as a least squares fitting term. which is quite common in other settings as well. And then we need to choose this regularizer, which some of you may also be familiar with, where it's some kind of penalty that puts a large value on images that are undesirable, maybe are noisy or maybe have other artifacts. And so we want to minimize the sum of these two to both get an image that agrees nicely with the data and also has a low penalty in terms of this, this regularizer. So that's the idea. So in SIL, we have different ingredients to handle all of this. And if we start by looking at the A part here, that is our model. We talked about that already. So we had the cases of the blurring operator. As we saw, we get a blurred image. The other one where you could mask out some pixels that you don't have access to, and you want to kind of fill those pixels in. And we had the CT case as well, where we measure something like this, lots of projections of this, or line integrals of this image, and then we want to solve that. So that's what our operators do. Next one, we have this fidelity term. As I said, this is kind of a data fitting term. And depending on what kind of noise we observe on our data, different systems will have different noise. We need to use different ways to measure this, different data fidelity. So the simplest case, if we have simple Gaussian noise, you can derive, it's kind of like a map estimate, maximum a posteriori estimate in a Bayesian context, if you like, but it's just this d-squares regression or fitting term. In SIL, we call that an L2 norm squared. You can also have other kinds of noise. I think maybe it doesn't show so clearly here, but if your noise is of the salt and pepper type, so basically black and white pixels that are added to your image, you need to use what's called a one norm instead, so measure things in a different way due to the noise characteristics. You can also have Poisson noise, and in that case, you need to use what's called the KL distance, the Kullback-Leibler divergence here. And all of these and more are offered by SIL, so you can kind of plug and play, try different fidelities out. We can also try different regularizers, and that's what the demo will do in a minute. So I won't show examples of that here. The last kind of component we need is, once we have specified everything, we end up having an optimization problem. So this optimization problem, we need to solve that. And depending on what kind of optimization problem we've set up, we do need to use a well-suited algorithm to solve that. So some problems are differentiable, some problems have other structure, and depending on all of that, we need to pick a suitable algorithm. And this is what SIL provides, a number of different algorithms. So there's some gradient descent algorithms, and we have one called FISTA, which I'll be demonstrating in the demo, and other ones that are suitable in various cases. I won't go into the details of that. I'll just say that we'll be using the FISTA algorithm in this demo here. Okay, so that's the second part of this demo. I'll jump right into that. So this was, if you recall, this was our blurred and noisy image, and this is now all we've got. We forget about the true image, and now we want to try and recover that. So as we discussed, we set up this kind of optimization problem. So we choose, since we know we added Gaussian noise, we pick this least squares simple term here, and then we have a look at trying out different regularizers to try and help us recover the image. Actually, the first thing we'll try is to ignore the regularizer and just say, let's try just and find the image that fits the data the best. So in SIL, we can specify these kind of mathematical objects, this function here. We have a least squares function object. So we specify the A part and the data here. We see it's this kind of least squares function object. And this is actually the cost function or the objective function that we want to minimize. So what we can do is we can, for example, look at what's the value of this function if we give it some image. So we could give it a blank image just full of zeros, and we see this is the cost or the objective for that particular image, 51,000 something. I don't know if that's big or small, but we could, for example, also give it the image of all ones and see what that looks like. Apparently that has a much smaller value, So this is in this setting, it's a better image. It has a lower value here. So what we want to do is find the image that causes this f to be the smallest. And this is what we need an algorithm for. So as I said, we use the FISTA algorithm. We need to specify, it's an iterative algorithm, so we start at this initial image, the 0 image here. We specify the cost function to minimize, how many iterations to run, and also how often to display information to the user on the screen. So we set that up, and then we can run it. We say, okay, maybe you start by running 10 iterations. And we see it runs, and we show the solution, and this is now what it looks like. And see, okay, we see some of the noise has gone or has been actually been smeared out a little bit more, and it's still kind of blurry. So okay, maybe we need to run some more iterations. So we do that, and the algorithm is just kind of paused. We can continue from where we left off and run another 90 iterations. And so the algorithm tells us a few things, how long it took for each iteration and how our objective is decaying. We see it's still changing quite a bit, so probably we haven't converged to the minimizer yet. The image, yeah, it just keeps getting noisier, it seems. It may be a bit sharper, I don't know, but it's for sure a lot noisier. So it's not great. And actually what will happen if you keep iterating, we see we will be reducing the objective. So we are solving the optimization problem as we intended, but we just keep getting more noise. And this is really the problem with these kind of ill-post inverse problems. The more noise you've got, and with these kind of operators, the noise will just come in and kill you like this. So basically, we need to do something else. And this is where regularization comes in. So we'll try different regularizers to kind of try and help us deal with this noise. And the first thing we'll try is what's called Tikhonov regularization. So we'll add a penalty term like this. So it's a squared 2 norm. So we set up another function object to do that. And the FISTA algorithm has 2 functions you can give it, and it tries to minimize the sum of these two. So it's the same call as before, just we have now this regularizer added. So we set up the algorithm, everything is like before, just with the G here, and we run it and see what happens. And it appears to converge. Now it's not making any progress after 100 iterations, and this is the image we get. So I'm not sure, but it seems that the noise is reduced, but it's still very blurry, still kind of blurry. And this is because Tikhonov is a kind of smoothing regularizer. It's like a smoothing filter. You will get rid of the noise, but you won't get any sharp edges. So it might be all right, depending on what you need to do with the image, but it's not really great. We'll try another one. We'll try L1 norm regularization, which is where you basically put a penalty on the sum of the absolute value of your pixel, and this is kind of a sparsity enforcing prior. So we set up everything like before and replace it just with this G term instead, and we run and we see, okay, it appears to converge also. It's not making any more progress. The value is a constant here, and this is what we get. So, not great either. It's okay, maybe it's a little bit sharper, but still super noisy. So it's maybe not the best either. Some cases it might be great, depending on if you have a very sparse image. This might be a really good regularizer. The last one we'll try is called total variation regularization, and what this does is it tries to enforce sparsity on the gradient image. So that's kind of like trying to enforce a piecewise flat image, so regions of constant value, and then just some jumps where you have edges. So it's kind of an edge-preserving regularizer. So we do this, and still offers the total variation function here. We set it up in the same way. This takes a little bit longer to run, but the principle is the same. We've just replaced the G here. Everything else is the same as before. We're running 200 iterations here. And we see that the objective is decaying. Okay, it's not decaying much more, so maybe it's close to converged now. It will just run a few more iterations. And what we'll see in a minute when it's done, we'll see that it's actually reduced the noise quite a lot. And at least for these large features, the edges are nicely recovered. As you move to the smaller features, it's really difficult for TV to distinguish what's noise and what's a feature, so it will tend to kind of blur things together. So for this image, it's a challenging one because you have these small features. But if you had just big regions, TV would be a really great prior. So it's just to say that depending on what your image looks like, you do need to use different regularizers. We can look at all of the different images, compare here at the end. So this was the kind of underlying secret unblurred image, and here's the blurred one, and here's when we solve it without a regularizer, just completely noise. And depending on our choice of prior or regularizer, we see we can get something smooth or something a bit sharper but still very noisy, or we can get this kind of piecewise constant, which does struggle a little bit with the small features. Okay. So for the next part, by the way, I think questions are being added to Slido. We'll take them at the end. Right, so for the next case, so this will be CT imaging, so computed tomography. So once again, we have an image. In the medical setting, it would be a patient in a CT scanner, and you spin an X-ray source and a detector around and acquire X-ray images all around. In material science, where I work, we normally have it the other way. So we have a fixed X-ray source and a detector, and we have a sample that we rotate on a rotation stage and acquire these projections. So it might look something like this. Up to the top left, we have a setup with an X-ray source to the left, and the rotation stage in the middle, and a detector to the right. And then we measure maybe a couple of thousand projection images, and then the task is to put all of those two-dimensional images together and determine this three-dimensional reconstructed volume. Here we scanned a walnut, and you could see nicely in different cross-sections, there's a vertical one and a horizontal one, all of the features inside the walnut. And with SIL, what this would look like, you'd read it in, and you'd apply some pre-processing steps, and we have tools to look at the data and see what kind of scan geometry we're using. And then we have a kind of the standard reconstruction methods people use all the time is called filtered back projection. So we have that, and this would do this, and then we could show the image. So we would show these couple of slices here. This is kind of the simplest workflow in SIL. Here's an overview of the module we offer. Some of these tools to the left are very CT imaging specific, so readers for different CT instruments, small lab instruments, and big synchrotron facility data sets, different kind of core data structures and pre-processing tools. And then in the fifth column, this optimization module, which I've been talking about with the algorithms and the different functions to allow us to specify optimization problems and so on. Also, we provide interfaces, the plugins to the far right, to some GPU accelerated toolboxes to do some of the heavy lifting for us. One is called Astra, one is called Tigre, and I added the reference there at the bottom for the software. Okay, so I have another demo, which will be over here. Oh, I think I need to go. Let's see. Switch this off. Here. So the first demo was kind of introductory to kind of show kind of a demonstration of some of the tools, and this is intended to be more advanced and more like this is how you could also work with a real data set and deal with some of the non-standard things you have to for this particular data set. So it's a so-called laminography setup. It means it's a little bit technical, but normally we would rotate about sort of like this upright axis here for flat samples that are difficult to image in this conventional geometry. We typically tilt the rotation axis and rotate about a tilted axis, and we can actually handle that in SIL here. So what we do is we read in, we specify basically the geometry, where is everything, where is the X-ray source, where is the object, how is everything tilted, and where are everything basically. So it's just setting up the geometry of the setup, and we hold that in this kind of cell acquisition geometry object, where you see we specify it's a cone and which angles and where's the detector panel and so on. And this is what we display, and we see it looks like this. So here's the detector, and here's the reconstruction volume we'll be solving for in a minute. The data are provided as a stack of TIFF files, and we have a TIFF stack reader. Here we crop some of the values away, and we only read part of the data to be a little bit faster. So only every 7th projection and crop it a bit. So we can specify settings like that and set up the geometry to fit that. So here's where we do the reading in, and we end up getting this acquisition data set, which we can then display in different ways. Here we're using our interactive slicer tool. I don't know if it works now. Yeah, you can kind of look at the different projections and see what this it's a sample. Let me just show you. I think I have, here's the paper where we did it. It's a test sample we built of Lego bricks to have a kind of nice and simple test image to look at. So we have these different layers of Lego blocks that we've put together and put in the scanner over here. Okay, and this is what one projection looked like, and you can look at different, as you rotate, different orientations, you kind of see all of the edges and the structures of the data set. So there are some stripes here. This is coming from the detector, which has some imperfections. We need to compensate for that by reading in what's called dark and flat fields, and we do here, and do a normalization of the data set. And the details don't really matter. It's just to say we kind of handle all the pre-processing steps. After that, all the stripes are gone. And the last thing we need to do is convert from the measured data, which is in what's called a transmission domain, to an absorption domain, which is essentially taking the negative log of the data. This is kind of the physical model, and it ends up looking like this. So this would be the data set as when it's ready for reconstruction, for solving the inverse problem. Okay, so let's see. I'm just going to skip that. So we'll start by doing kind of the conventional type filter back projection reconstruction, a variant called FDK here. So we set up everything to do that. We do need to do some reordering of the data here because we're using this toolbox, which needs data to go in a special ordering. So we do that first. Then we set up the volume for us to reconstruct onto, and then we apply the reconstruction algorithm. And this is what I think is a little bit difficult to see here. I think I changed the display. Was it in this one, maybe? Anyway, so you're meant to see like a kind of faint reconstruction, kind of dark gray reconstruction. This is a kind of, it's a fiducial marker, so it's a marker we put in there, high contrast, to help us align the images. We can do some further cropping and so on to make it a bit smaller. So let me just get further down here. Okay, so we've reconstructed a 3-dimensional volume now. Here I changed the contrast so you can see it a little bit better. So you see in the kind of the flat direction, you see the Lego structure here. It's not completely aligned. That's why it looks a little bit different. It doesn't. And here you see some of the other layers. If you look at the vertical cross section instead, and I think it's not too clear here, but you'll see you have these kind of streaks or blurred bits coming from the top and bottom of all of the features here. And this has to do with this tilted geometry. So the question here was, how do we deal with that? Can we somehow compensate for that through use of regularizers? And we try different things. Basically, we try the same methods I showed you for the deblurring case. And the nice thing is that once we've set up the operator and we can specify the optimization problem for this 3D CT scan in the completely same way as we had for the deblurring case. So what we do is we set up an operator, just like we had the blurring operator before. We now have the model for how the projections arise from the image, and we set up again this least squares and try just running a least square, so no regularization. And we run it again with the Vista, just like before, and we see we can reduce the cost function here quite a bit. and this is what the reconstructed image looks like. We didn't add any regularization yet, and actually this makes sense. We see we still have these kind of diagonal stripes or blurred bits down here. So here what we'll do is we'll try the TV regularization again. Remember, we saw it was working quite well to help us preserve edges, at least of kind of large features. So we'll do that again here, see if that's helpful. Here we use a faster version of the one we had before, which uses the GPU to accelerate computations, but otherwise it does the same thing. So we set up this is what we called G before. This is our TV function. And then again, we set up the FISTA algorithm with the different components, the initial value to start from, the least squares, the TV penalty term, and how many iterations to run, and so on. And we see we reduce the objective quite a bit, and it's kind of slowing down here. So it's not quite converged, but it's getting close. And this is what the images look like. And in particular, if you look in this vertical dimension here, you see that we now have much more well-defined edges here. Before we had these diagonal streaks or stripes and some blur around, and that's completely gone now. So the TV regularizer helped us to compensate for this for the challenging data set here. And in the end, we can compare all of the different ones. We had the standard method over here with the stripes here, and the least squares without regularizer here, and the TV here to the right. And again, we see that we are compensating for the problems and getting much sharper edges here. Okay, so let me move on to show a few more case studies we've done. I think I need to switch this here. So in particular, we're interested in cases where we have another dimension. So the simplest case perhaps is if you have an image that's a color image, and you have 3 channels, red, green, and blue, and basically you have kind of a gray image in each of these channels with slightly different values. And so together they form this color image. So up until now, I've only talked about applying a regularizer kind of within the image, but having this extra dimension, we can also look at enforcing regularity across these channels. So SIL allows us to do different things here. For example, we have a case where this is the Inpainting case. So we start from this corrupted image with parts missing and noise added, and then we try different methods. We try a variant of TV that I showed you before. This is called TGV. And it's a little bit better for when you have a smooth image. I think you can't maybe see so much difference between the two, but at least you see we're able to fill in the blanks and get a nice recovered image. Here we use another algorithm, the PDHG algorithm, which is an alternative to FISTA, if that's a little bit more flexible. And the details are in the paper at the bottom there. We are also interested in time-resolved imaging, so studying components as they change over time. Maybe you can have some process happening and you want to study that over time. This is a little bit difficult normally because it takes maybe 1 hour to acquire one data set, which means it's difficult to get any good time resolution, right? A lot of stuff can happen while you acquire that one data set. So what we try to do is say, okay, let's acquire the data a lot faster. So maybe we acquire not a couple of hundred or a couple of thousand projections, but just 18 projections. And if we use the normal reconstruction method, we see we get lots of streaks and lots of noise, and we can't really see the features of what we're looking for here. We put together a new regularizer in SIL, which we call the directional total variation regularizer. And from the same data set, we're able to get this kind of reconstructions here, where we see the features a lot better. And this does regularization, trying to use some edge structures and propagate them across the channels, basically. So it's an example of how we use more information than is just in one image. And this you can't do with the kind of conventional method. Another case is where we have an energy discriminating detector. So normally the photons or neutrons or whatever you're measuring with, the energy is not recorded by the detector, but we have new detectors coming out now where we can actually measure precisely the energy of different photons. And this is nice because we have different responses at different energies. So if we have a data set here acquired at a neutron facility in the UK. And if we just look at we have about 3,000 different energy channels. If we just look at the data for one such energy channel, we have very few photons, so very noisy data, and we get this kind of reconstruction up here, which is very noisy, and you basically can't tell these big cylinders apart here. We looked at a couple of different new regularizers. One is called total nuclear variation, and one is called TGV. This is where we do TV kind of in the spatial dimension, and this other thing, TGV, across the channels. And we're able to get much sharper cylinders and identify the materials a lot better across all of the channels here. We have also worked with people who are not doing X-ray imaging, but PET and MR imaging, which is a little bit different. And here you also have some motion that you need to estimate along the way. We're able to formulate a reconstruction problem in SIL that takes this motion into account and go from this kind of uncompensated image to the left here to it's a little bit over smoothed, I think, but the edges are a lot better preserved and the noise is reduced a lot over here. And another case where we have a feature that with the normal reconstruction method was very blurry, and we see we're able to get the edges sharper, not completely sharp because the resolution is not great, but you can see there's a feature here that's not visible to the same extent over here. Okay, so we run a number of different activities. We have some training events. People from the community are participating. Here this was the only in-person activity we ran before COVID, and we've run online sessions. We have another one coming up. And okay, what happened here? So there's a sign-up link if you're interested there. And other than that, I'll just summarize here. So we have SIL is an open source Python library for solving inverse problems, specifically for imaging type problems. And in particular, we have worked a lot with challenging CT image data sets, so very noisy, low count data, time resolved, non-standard imaging setups, and multi-channel type images. It's highly flexible. As you can see, we can kind of put together different regularizers, different data fidelities, and use different algorithms to solve the problem. We have a close to math, near math specification, like how the code looks almost like the math, which helps specify these optimization problems. Normally, you'd need hundreds of lines of code maybe to set that up. And hopefully, people will find it simple to get started and still expressive enough to actually, and powerful enough to solve big real problems. There's the website, we have documentation and different repositories. We've started a Discord, and you're welcome to contact me at the email address there. Thanks very much.
So thanks, Jakob, for the wonderful presentation. So I'm going to now repeat some questions from the Slido. First one is, you often don't know what kind of noise you're dealing with. Often also different kinds of noise overlaying. How do you determine the regularizer?
Yes, that's a really good question, and I think you can take different approaches there, and you can either just sort of say, okay, I don't know what it is, and try different combinations of the tools we provide and see which one kind of empirically gives you the best reconstruction. Or you can try and investigate your noise, so look at some background regions where you have just air, where you have kind of just the noise signal, and try and determine what kind of noise is there, and then based on that choose your data fidelity and a suitable regularizer.
So it's like basically just trial and error, and based on your experience?
There is some trial and error aspect to it, but also you can try and see if you can actually determine from the data what kind of noise type it is.
Great. Okay. Second questions. Is there anything in CIL to facilitate, optimize the choice of regularization parameter, or is it all? I think it's the same question, right?
It's I think it's a related question, and it's a really good one, and it's something we'd like to put in there. So we have, and I didn't talk so much about that. There's this regularization parameter that governs the trade-off between how much emphasis do you put on fitting the data and how much emphasis do you put on your penalty term. And this is a parameter you do need to choose. At the moment, we don't offer any tools to determine the best one. So the typical thing people do is they do a search or a sweep and pick the best one. There are tools in the literature, but we haven't seen any of these tools are kind of robust enough to put out there. But if there are some ideas, I'm curious to hear about what that could be.
Which are the most important libraries under the hood of CIL?
So I would say, these data sets, especially the micro-CT data sets I showed, the laminography one, it's a couple of gigabytes, so it's quite big data sets, reasonably big, and there's a lot of heavy lifting in computing basically solving the direct problem and what's called the adjoint problem also. And to do that, we need to use GPU acceleration, and we use the Astra toolbox, which is another open source tool, and another one is called Tigra. And we provide a unified interface so you can choose either, basically. So I think those are two important packages to mention that we rely on.
Regularizer seems to encode knowledge of the domain and setup. Is there any structured way to encode that knowledge, or is it just intuition and trying them out?
Can you repeat that, please?
Regularizer seems to encode knowledge of the domain and setup. Is there any structured way to encode that knowledge, or is it just intuition and trying them out?
I mean, there's some. I think there's a lot of experience that goes into that, but there is some theory behind it. Like, for example, this one norm, you can show theoretically that it's a sparsity enforcing prior, so it will tend to push a lot of values all the way down to 0, and preserve only a few values. And if you know you have a sparse image, so this could be kind of a foam structure where there's a lot of air and just a few pixels that are non-zero, you would expect that kind of prior, that kind of regularizer to be suitable for this kind of case. So I think it's a bit of both. It's a mix of theoretical expectations and also some trial and error and experience.
What is the main benefit of the noise reductions? Is it true to say that deep learning models will learn to remove noise by themselves?
So there's a lot of work on deep learning also coming into inverse problems at the moment. And many cases are showing that deep learning type reconstruction methods can substantially reduce the noise and help solve some of the same problems. Sometimes better than what we can do with these kind of methods. But oftentimes the challenge is getting training data. Oftentimes we scan just one thing, and the next thing that comes in looks completely different. So obtaining good training data is not so straightforward here.
So it's the data that matters how the models perform, right? In the end.
I think if you were to set up a deep learning model, it relies a lot on the training data you would feed it with.
Okay. Yeah, that's kind of the thing. Okay. I think the time is almost up, so I think we can take one questions from here. So if anyone have any questions, you can pass the mic. Oh,
okay. Thank you. Maybe as a follow-up to the last question on using deep learning, couldn't your tool be used to generate good synthetic data for those training cases? Like, for example, adding all these different kinds of noise?
So the question is, can you create synthetic training data? and develop your deep learning method.
Yep.
Yes, this is an approach people take with some success, but again, depending on the setup, and for example, this tilted case where you have another setup, you probably need to do training data set specifically for that case, and there will be parts of well, there's a discrepancy between what you can do with simulated data and the real data you measure, and it's not completely clear if it's enough to base it on simulated data. But it's something that people are looking into.
All right, thank you.
All right, I think the time is almost up. So let's give it up for Jakob again.
Thank you. Thank you.